Hello students, today we are going to discuss about the topic of system properties, which is very important in the examination. So it belongs to the subject of signals and systems, applicable for all three branches of electronics and communication and electrical as well as instrumentation. So before going into this particular topic of system properties, first of all you have to know what is the definition of a system, general representation of a system, and the basic terminology that we follow to represent a signal. Basic representation of signal, so both continuous time and discrete time. And of course you should have a fair amount of idea of the topic that we have already discussed, and it is available in the videos Transformation on Time. So first of all, we'll look into the definition of a particular system. Now, what is a system? You can question yourself, what is that entity that we call as a system? We know that a system is something which does some useful work. A system is something that is going to do some work in a way that if we provide an input, the response of the system or the output of the system is going to be the desired one. It is not any output. If it is any output, probably we could not call it as a system. Only when it is a desired output. For example, if it is an amplifier, then the system should produce an output which is going to be a strengthened version of the input. So a system is something which is going to do some useful work. So general representation of the input is going to be x of t or x of n, and the output is going to be y of t or y of n. This is my system. Now what is x of t, x of n? What is the difference between both of them? One of them is going to be continuous time signal, the other is a discrete time signal. General representation of a continuous time signal will be with open brackets. You are going to have a t, a small t, which is going to indicate a continuous time signal. Whereas a discrete time signal is going to have a closed brackets. So the closed brackets, and in the brackets you are going to have small n. So both small t and small n are the indicators of time. So it is going to indicate the time in the x-axis, and the signal is going to be in the y-axis. So that is the general representation of a continuous time signal and a discrete time signal. Now when you are giving x of t as the input, then the response is expected to be y of t. Similarly, in the case of a discrete time, if the x of n is given as the input, then the response is expected to be y of n. Okay, so a system is something which is going to do the useful work. And how is it going to do the meaningful work? It is done by processing the input to get the desired output. So system is one which is going to process or manipulate the input, and it is going to give you the desired output, and it is also a meaningful connection of devices. System is going to be a meaningful connection of devices. So it is going to have a one or more inputs and one or more outputs. That is what is all about the system definition. Now we can have different types of systems. As example, it can be a control system where it is going to control one of the parameter. It can be a communication system. So there can be different types of systems. Okay. Now looking at the representation of the system. System can be represented in many ways. System can be represented either using a differential equation, or it can be represented using a transfer function, or it can be represented in terms of state variables, or it can also be represented in terms of an impulse response or step response. So in the subject of signals and systems, we will emphasize a lot on representation of system using an impulse response. Right? So that is what is the representation of system all about. We have already seen the basic representation of signal in terms of continuous time and discrete time. Continuous time, you're going to use a small brackets, open brackets. So x of t. So the brackets are going to be open brackets. In the case of a discrete time signal, you're going to have a closed brackets. That is the difference between a continuous time signal and a discrete time signal's representation. And the last one is something that we have seen in a different video. So please go through that particular video before attending this particular lecture. So here we are going to learn about different properties. We're going to start with the property called as memory. And then we will discuss about something called as invertibility. We will discuss about something called as causality. And then stability, linearity, and at last we're going to see time invariance. These are the 6 important properties which are very, very important for examination. So based on memory, we classify the systems into static and dynamic systems. Based on the property of memory, we classify the systems as a static system and dynamic system. Based on invertibility, we can classify the systems as invertible and non-invertible systems. Okay, based on the causality property, systems can be classified as causal and non-causal. Based on stability, of course, as stable and unstable systems. Based on linearity as linear and non-linear systems. And at last, based on the property of time invariance, we classify the systems as time invariant or time variant systems. Time invariant and time variant systems. So these are the 6 properties that we are going to learn. First, we'll start about the static and dynamic systems. We'll start with static and dynamic systems. So, static and dynamic systems. Now, what is the meaning of a static system? A system which does not require any memory for its work is what we call as a static system. Or a system which does not have any memory is what we call as a static system. So static system is one which does not have any memory. The moment it has a memory, we call it as a dynamic system. So a dynamic system is one which is going to have a memory. So based on memory, if it has memory, we call it as a dynamic system. If it does not have any memory, we call it as a static system. So what is the example? First of all, let us look at the example for a static system. The output y of n is given as equal to x of n minus 2 into x of n squared. Now, here we have a relation between the input and the output. So x of n is going to be a discrete time or continuous time signal. Okay, as we have seen, whenever there is a closed brackets and in the bracket we have n, it is going to be a discrete time signal. So y of n is equal to x of n minus 2 into x of n whole square. Okay, 2 into x of n square. So such a system is an example of a static system. Why it is a static system? If you take the value of n is equal to 0, the output that I am going to get at n is equal to 0 is y of 0 is equal to x of 0 minus x square of 0. Y of 0 is equal to x of 0 minus x square of 0. So for y of 0 as the output, x of 0 is going to be the present input. Something which is before x of 0 are going to be the past, after that are going to be the future. Correct? So if I take the x of n, if there is a 0 here, this is going to be the present value, and 1, 2, 3, I mean to say x of 1, x of 2, x of 3, those are going to be the future values, and x of minus 1, x of minus 2 are going to be the past values. Now you can see that the output y of 0 is going to be only depending on the x of 0, which is the present value. It is neither depending on the past value nor it is depending on the future value. Such a system is what we call as a static system, because It does not require any memory because there is no requirement of past values and the future values. So such a system is going to be a static system. So this particular system is going to be a static system. So if you have a y of n is equal to x of n minus 1, this is one of the system. Y of n is equal to x of n minus 1. At n is equal to 0, y of 0 is going to be equal to x of minus 1. So when you want a y of 0, it is not depending on x of 0, rather it is depending on x of minus 1. It is depending on x of minus 1. So x of minus 1 is going to be the past value. For example, the present is present at n is equal to 0. For n is equal to 0, n is equal to minus 1 is going to be the past value. So here, the system is depending on the past value of the input. Similarly, if you consider n is equal to 1 as the present value or a present instant of time, then y of 1 is going to be the present instant of output. And x of 1 is going to be the present input of input, present instant of input. So, but y of 1 is going to depend on x of 0. If x of 1 is going to the present instant of input, x of 0 is going to be the past value. The moment you consider n is equal to 1 is going to be the present instant. For n is equal to 1, n is equal to 0, n is equal to minus 1 and so on are going to be the past instants. N is equal to 2, n is equal to 3 are going to be the future instants. So, y of 1 is going to be the present output. For that, x of 0 is going to be the past input. So here the system for its function is going to depend on the past value of the input. So this particular system is going to be an example of a dynamic system. Now similarly, y of t is going to be integral of minus infinity to t x of tau d tau. It is an integrator basically. Now what is this particular system? Is it going to be a static system or a dynamic system? An integrator, is it going to be a static system or is it going to be a dynamic system? Integrator is going to be a dynamic system. Why? For example, let me consider x of t. This is time, this is x of t, the signal. Right? So the x of t probably is going to be represented. Now the signal is going to be something like this. Now what is the output? Output y of t is nothing but the integrated version of the input. So now for a system, if you give the input as x of t, the system is going to give the output as y of t. And we know the y of t is nothing but integral minus infinity t x of tau d tau. Now if you observe, if I consider t is equal to 0 is going to be the present instant. T is equal to 0 is somewhere here. So t is equal to 0 is going to be the present instant. So then y of 0 is going to be equal to integral of minus infinity to 0 x of tau d tau. So if you want the y of 0, you require the instance of x of t from minus infinity. Minus infinity is going to be the left extreme of the signal. So from minus infinity to the value of x of 0, you want each and every instant. And we know if t is equal to 0 is going to be the present instant, t less than 0 is going to be the past instance. So if you want to calculate y of 0, you require all the past instants of x of t. You require all the past instants of x of t along with the present instant. Correct? So it is definitely going to be the dynamic system. It doesn't matter whether it is going to depend on the present, the past or future, whenever it is depending on some memory. Except the present, if it requires either past or future, it is definitely going to be a dynamic system. So here, the integrator is an example of a dynamic system. Right? It's very, very simple. If it depends only on the present value of the input, then it is going to be a static system. The moment it depends on the past value or the future values of the input, then it is going to be a dynamic system. So that is how we have a classification of a static system and dynamic system. Now the second important property is invertible and non-invertible systems. Right. So invertible and non-invertible system. What is the meaning of invertible and non-invertible? We have seen that based on the topic called as invertibility, based on the property of invertibility, we can classify the systems as invertible and non-invertible systems. Now, to understand the concept of invertibility, let us take two systems. System 1, which is cascaded with another system, which is system 2. The input of the system 1 is x of t. The corresponding output of system 1 is y of t. So y of t is given as the input to the system 2, and the output of it is going to be equal to w of t. So x of t is the input, y of t is the output of the system 1, and output of the system 2 is going to be w of t. Okay. Now, using the output of the system 1, which is y of t, I am getting the output of the system 2, w of t. Now, if the w of t, if it is equal to x of t, what does it mean? X of t is the input of the system 1, and the output of the system 1 is y of t, and which is given as the input to the system 2, whose output is going to be equal to w of t. Now, what I am saying here is that if w of t is equal to x of t, what does it mean? It simply means that system 2 is doing the completely opposite work of the system 1. The system 1 is producing y of t from x of t. And now from y of t, I am once again producing x of t. Correct? It means that system 2 is doing the opposite function of system 1. Now that is what we call as the invertibility. If it is possible to get the value of w of t is equal to x of t, then only we can say the system 1 is going to be invertible system. Why are we calling system 1 as invertible system? Because from the output that it is generating, it is possible to get back the input using any other system. Using any other system, it is possible to retrieve back the input x of t. That is why this particular system is called as an invertible system. Okay, I'll repeat once again. System 1 is said to be invertible whenever, if it's possible to get back the input of system 1 using the output of the system 1. That is what we call as a invertible system. So system 1 is then said to be a invertible system. Okay. So for example, if I have the output y of t is equal to that of x square of t. Output y of t is going to be equal to that of x square of t. I have to say whether the system is going to be invertible or not. Okay. So x of t is nothing but the input and y of t is nothing but the output of the system 1. Now I want to say whether this operation of the system 1 is going to be invertible or not. Okay. What are the general applications of invertible systems? Did we find any invertible systems in practical life? There are so many examples. So what are the examples? Maybe we can consider modulator, demodulator. It can be multiplexer, demultiplexer. It could be encoder, decoder. Like that, there are so many examples where we require an invertible system. Modulator does some operation and demodulator has to do the opposite operation of the modulator so that it can get back the same input. Okay, whatever input that you are supplying for the modulator, the same you require as the output to the demodulator. So we have a good number of examples. Let us test y of t is equal to x square of t, whether this particular system is going to be invertible or not. Now x of t is going to be the input values of system 1 and y of t is going to be the output values of system 1. Now for example, x of t is equal to 0, the output y of t is also going to be equal to 0. X of t is equal to 1, the output y of t is also going to be equal to 1. X of t is equal to 2, the output is going to be 4. X of t is equal to 3, the output is going to be 9. Similarly, x of t is minus 1, the output is 1. X of t is minus 2, the output is 4. Now, this is the relation that we have, right? For 0 you are getting 0, for 1 you are getting 1, for 2 you are getting 4, for 3 you are getting 9, for minus 1 also you are getting 1, for minus 2 also you are getting. Now you have a y of t at the output of system 1, which you are going to provide as an input to system 2, so that I am getting the value of w of t as the output to the system 2. So here is what we passed through system 1, now we are passing through the system 2. Now if you observe, when you give the input as a 0, what should be the output? X of t. So when I give 0, 0 I want. When I give 1, I require 1. When I give 4, I require 2. When I give 9, I require 3. When I give 1, I require 1. When I give, minus 1. When I give 4, it's going to be minus 2. Now you just look at the game here. Whenever I give 1 at the y of t, the w of t can be 1 or minus 1 for the same value of y of t. Now, how can a particular system predict whether it is going to be 1 or minus 1? What I am saying here, you can see that both the inputs of system 2 are 1. Both the inputs of system 2 are 1. But the output should be x of t, right? It means that in the first instant it should be 1, in the second instant it should be minus 1. Now how can the system decide whether it is going to be 1 or minus 1 when are giving 1 as the input to the system 2? How do you think it is possible for the system 2 to say that the output is going to be 1 or minus 1 for the same input as 1? There is no possibility for a system to 100% say that it is going to be 1 or minus 1. It means that there is an ambiguity at the system 2. So whenever there is an ambiguity, whenever the system is not successful, I mean to say the system 2 is not successful to identify whether it is going to be 1 or minus 1 for the same input as 1, then the system is going to be a non-invertible system. When the system 100% says it is going to be a particular output, then definitely it is going to be a invertible system. Ultimately what I require is that the w of t, it should be equal to that of x of t. Whenever it is possible from the value of y of t to get back the x of t, system is going to be invertible. Otherwise the system is not going to be invertible in nature. Now if you have still some confusion, let us look at the examples so that it becomes a little bit more clear. So we have looked at a particular example where y of t is going to be equal to x square of t. Is a x square of t, and we have decided that the system is going to be a non-invertible system. Now let us look at another example. Y of n is equal to 2 into x of n. Y of n is equal to 2 into x of n. So I have an x of n. Correspondingly, when I pass through system 1, it is going to give me y of n. And when I am passing through the system 2, it is going to give me w of n. When the input is 0, then what is the y of n? Y of n is going to be 2 into x of n. It is also 0. When the input is 1, it is 2 here. When the input is 2, it is 4 here. When the input is 3, it is 6 here. Similarly, when it is minus 1, it is going to be 2 here. When it is minus 1, it is going to be minus 2 here. When it is minus 2, it is going to be minus 4 here. When it is minus 3, it is going to be minus 6 here. And now from system 2, the output should be equal to that of x of n. It means that it should be 0 here, it should be 1 here, it should be 2 here, it should be 3 here, it should be minus 1 here, it should be minus 2 here, it should be minus 3. Okay, so when it is 0, the output is going to be 0. When it is 2, the output is 1. When it is 4, it is going to be 2. When it is 6, it is going to be 3. When it is minus 2, it is going to be minus 1. When minus 4, it is going to be minus 2. Minus 6, it is going to be minus 3. So there is no ambiguity here in this particular case that for a particular input of the system 2, the output are going to be many. There is no ambiguity like that. Whenever I have 2, the output has to be 1. There is no other value that is available. So here the system is going to be an invertible system. Now the system 2 is nothing but W of n is going to be equal to that of Y of n by 2. So if I have a system 2 which performs the operation of W of n is equal to Y of n by 2, so of course it is going to be the invertible system, because 0 by 2 is going to be 0, 2 by 2 is going to be 1, 4 by 2 is going to be 2, 6 by 2 is going to be 3. So this particular system is going to be an invertible system, because there is no ambiguity at all. If you want to realize the output which should be exactly same as that of the input of the system 1, there is no problem. We are able to do that. Therefore, the system 1 is going to be an invertible system, because from the output of system 1, we are able to get back the same input of the system 1. That is why system 1 is going to be called as a invertible system. Right? We have looked at two systems. The first one was a non-invertible system. The second one is a invertible system. Now, what is that particular property by which we can directly say that the system is going to be either invertible or it's not going to be invertible? There is a one property by which we can directly say whether it is going to be invertible or non-invertible. That is that whenever the distinct input is going to lead to distinct output. When a distinct input leads to the distinct output, the system is always going to be invertible. We might have learned about a one-to-one mapping, right? So whenever there is a one-to-one mapping between the input and output relation, definitely the system should be an invertible system. Okay, so that is what we have to keep in mind whenever we are checking the invertibility of a particular system, that there should be one-to-one mapping between the input and output. The distinct input should always lead to the distinct output. So let us look at some example. Y of t is equal to sin t into x of t. Y of t is equal to sin t into x of t. We have to see whether this particular system is going to be an invertible system or not. Okay, you can pause the video and try to check it. Okay. So x of t and y of t. Now let me consider the value of x of t is x of 0. Then what is the output? The output y of t is sin 0 into x of 0, which is 0. Now, if t is equal to 2 pi, x of 2 pi, sine of 2 pi into x of 2 pi, which is also equal to 0. Now you see that for two different values of the input, I have the same value of the output. For two different values of the input, I have the same value of the output. Then whenever this happens, it is going to be this is definitely going to be a non-invertible system when two different inputs have the same output. The problem was easy because it is a trigonometric relation. So I want to see for which value of the input the output should be the same. Okay. So that is how we generally test the invertibility of a particular system. So here the system is non-invertible in nature. Now let us discuss about the next property based on which we can classify the system as causal and non-causal systems. So based on the property of causality, we can classify the system as a causal and non-causal system. Now what is a causal system and what is non-causal system? A system is said to be causal whenever the output depends only on the present and past values but not on the future value. The moment it starts depending on the future value, it is going to be a non-causal system. Okay? For a system to be causal, it should not depend on the future value of the input. The moment it starts depending on the future value, it is going to be a non-causal system. Okay. So causal system is one doesn't depend upon future value of the input. Okay. If it depends, it's going to be the if it depends, it's going to be the non-causal system. A causal system can only depend on the present and also the past values. It should not depend on the future values. Now, have you looked into a particular system which depends on the future values? Is there any system like that where the output of the system is going to depend on the future value of the input? Have you seen any system like that? No, right? So, it is not generally possible to have a non-causal system because every system that we use is something that is going to use the present value and the past values. Okay, so all physically realizable systems, but this particular statement is only half true because all physically realizable systems are causal only when the input is not recorded. Okay, when the input is recorded, then it is possible to have a non-causal system. Okay, all physically realizable systems are causal when input is real-time input. I mean to say here real-time. All the physically realizable systems are causal when the input is not recorded or when the input is real-time. The moment it is going to be recorded, then definitely it is possible because the tape recorder, we can definitely access past values or also the future values because we have already recorded the inputs, right? So whenever you have recorded the inputs, then it's not a problem at all, okay, to access either the past value or the future values, right? So in the case of recorded inputs, it is possible to have a non-causal system. It is possible to have a non-causal system. Okay, so let us see some mathematical relations between the input and output so that we can say or judge whether a particular system is going to be causal or not. The output y of t is equal to x of minus t. Y of t is equal to x of minus t. We have to check whether this particular system is going to be causal or not. You can pause the video and try to do it. Yes, students. Let us check whether the system is going to be causal or not. Let me consider the value of t is equal to minus 1 as a present instant. So when I consider t is equal to minus 1 as a present instant, right? So y of minus 1 is equal to that of x of 1. If I consider t is equal to minus 1 as a present instant, x of minus 1 is going to be the present instant of the input and y of minus 1 is going to be the present instant of the output. And for t is equal to minus 1, t less than minus 1 are going to be the past values. These are going to be the past values and the right side are going to be the future values. Okay? The right side are going to be the future values. Yes or no? So, y of minus 1 is depending on x of 1, which is the future value. So, whenever it depends on the future value, it is going to be the non-causal system. You can ask me the question for t is equal to 1, y of 1 is going to be equal to x of minus 1. So, if I consider x of 1 or 1 as t is equal to 1 as a present value, present instant, then the left side is going to be the past and the right side is going to be the future. Then y of 1 is depending only on the x of minus 1, which is the past instant of the input. Then you can ask me that, yes, here it is depending only on the past value, then why did you say it is going to be non-causal? The thing is that even once it fails, or even once it is depending on the future value of the input, then definitely we are going to term it as a non-causal. It doesn't mean that non-causal system is only going to depend on the future value. It can depend on the past value for some instance of time. For here example, t is equal to 1, it is depending on only the past value. But for t is equal to minus 1, it is depending on the future value, right? So even for one instant, if we see that it's going to depend on the future value, it is going to be a non-causal system. So therefore we judge this particular system as a non-causal system. Let us take any other example. Y of t is equal to integral minus infinity to t x of t tau. Whether this particular system is going to be causal or not. You can pause the video and try to solve it. Okay, so let us consider a particular input and let us select this particular instant. So this is going to be the present instant. Left side is past, right side is future. So for t is equal to minus 2. For t is equal to minus 2, y of minus 2 is going to be integral of minus infinity to 2 into minus 2 x of tau d tau. Integral minus infinity to minus 4 x of tau d tau. Now where is minus 4? This is minus 3 and somewhere here minus 4. Let us extend this one. So the output at t is equal to minus 2. If I consider t is equal to minus 2 is going to be the present instant. Y of minus 2 is going to be the present instant of the output. X of minus 2 is going to be the present instant. So for t less than minus 2 is going to be the past. T greater than minus 2 is going to be the future. Right. So if that is the case, whenever you are integrating the input from minus infinity to minus 4, minus infinity to minus 4, it means that the left extreme to minus 4 if you are integrating. For t is equal to minus 2, all these values are going to be the past values. So when the output is depending on the past value, it doesn't matter, it is going to be here, it is causal, no problem. But now, let me take t is equal to 2. Then y of 2 is going to be integral of minus infinity to 4 x of tau d tau. Now in such a case, t is equal to 2 is going to be the present value and this is past. The right side is going to be the future. And what is our future? 3, 4 and so on. So t less than 2 is going to be the past and t greater than 2 is going to be the future. Now if that is the case, all the values till t less than 2 are going to be the past, t greater than 2 is going to be the future. Now y of 2, the present instant of the output, is depending on the values of the input from minus infinity to the value of 4. From minus infinity to the value of 4, it is depending. Now there is a problem. From minus infinity to 2 are going to be the past values, t is equal to 2 is going to be the present value, from 2 to 4 it is going to be the future value. Here you can observe that if you want to get the value of y of 2, it has to depend on the future values. Now you can say that it is not depending on this, okay, I will not consider this particular part, I am only going to consider this particular part. The answer is wrong, right? Because the operation is that integral minus infinity to 2t. So if you want to perform this operation, you have to depend on the future values to some extent. So it is not satisfying the causality. Right. So this particular thing, even though here it is satisfied, but I am going to say this particular system is going to be a non-causal system. System is going to be non-causal for the simple reason that there is an instant where I can see that it is going to depend on the future value. Okay, now let us look at the another property, which is stability. So based on the stability, we can classify the systems as stable and unstable systems. I can classify the systems as stable and unstable systems. So to understand this particular concept of stability and instability, I want to know about what is a bounded signal. Because if you don't know what is a bounded signal, you will not understand the stability. First of all, I'll try to understand what is a bounded signal. I'll give you some examples, and you yourself say whether it is going to be bounded or not. Maybe a sinusoidal signal, a step signal, a ramp signal, an exponential increasing signal. So these are the 4 signals that I have selected, and maybe a rectangular pulse. So I have given some set of 5 signals, right? Which of them are going to be bounded and which of them are going to be not bounded? And just think about it by pausing the video. Now, so sin t is an example of a bounded signal. R of t is an unbounded signal. Rect t of t is a bounded signal. U of t is a bounded signal. Unbounded signal. What is the criteria? That any signal that you are considering, if I consider it as an x of t, the amplitude of the signal should always be less than infinity, no matter what is the value of time. Because time is an independent variable, it can vary from minus infinite to infinite. But the signal value should never touch infinity. The magnitude of the signal value should never touch infinity. The mod of x of t should always be less than infinity. Such a signal is what we call as a bounded signal. Now for example, if you see sin t. So sin t is only going to vary between the of minus 1 and 1. The amplitude is always going to vary between the of minus 1 to plus 1. Rectangle t, so it's a constant value. Okay, if between a particular time it is going to be a constant, otherwise it is going to be 0. So I don't have any problem here. Ramp signal, it is going to be an unbounded signal because at t is equal to infinity. Is it possible to take t is equal to infinity? Yes, I can play with the independent variable. When you are increasing your value of time, the signal value is also going to be increasing. It means that when the time value is going to be very high, probably infinity, here the output is also going to be, the signal value is also going to be infinity. So definitely it is going to be an unbounded signal because there is one instant where it is going to touch the value of infinity. Right? So this is going to be an unbounded signal. Now what about u of t? U of t is going to be a bounded signal because the value is always constant, which is equal to 1. On the right side of t is equal to 0. For u of t is equal to 1 for t greater than 0, and it is equal to 0 for t less than 0. Nowhere it is touching the value of infinity, even though time is going to touch infinity. So don't have any problem here. E power at into u of t. It's an exponentially growing signal for t greater than 0. So you can see that here it is going to be an exponentially growing signal. It means that at one point it can touch the value of infinity. So this is the concept of a bounded signal. Please don't confuse between the of a bounded signal and a finite duration signal. A bounded signal, it means that amplitude should never touch infinity. Whereas a finite duration signal is something which is different. A finite duration signal is one where the duration of a particular signal should always be finite value. If you see sin t is going to be from minus infinite to infinity. U of t, the signal will be there from 0 to infinity. So it is going to be a infinite duration signal, but it is a bounded signal. Okay, both sin t and u of t are going to be the bounded signal, even though it is going to be an infinite duration signal. So should not confuse between that of a bounded signal and a finite duration signal. Now based on the concept of a bounded signal, we can classify the systems as a, okay, this is what we are going to use as a very important criteria to test whether a particular system is going to be stable or not. Now that particular criteria is what we call as a bounded input, bounded output criteria. The criteria is known as a bounded input, bounded output criteria. Now what is this particular criteria? If you are considering a particular system, the input is x of t and the output is y of t. Right? For each and every value of the bounded input, the output should also be bounded in nature. What did I say? For each and every value of the bounded input, the output should be bounded in nature. Such a system is what we call as a stable system. Such a system is what we call as a stable system, satisfying the behaviour criteria. For each and every bounded value of the input, the output is going to be bounded. Now for example, let me take some 100 inputs. I have seen that for 99 inputs, the output is also going to be bounded when 99 inputs are also bounded in nature. Okay, for 99 bounded inputs, the output is also going to be bounded in nature. But for the 100th bounded input, the output is going to be unbounded in nature. Can I say the system is going to be stable? No, I cannot say the system is going to be stable. The system is an unstable system because it fails. Okay, at one instant it is going to fail. For one particular input, it is going to fail. System should be mercilessly told as a unstable system. Even though for 99 inputs, for 99 bounded inputs, the output is going to be bounded. For a single bounded input, if the output is going to be unbounded, still the system is going to be unstable system. Right? So therefore, that is the concept of a unstable and stable systems. Now let us take some examples to check whether it's going to be, which of the following systems are going to be stable and unstable. The first one is y of t is going to be equal to x square of t. Y of t is equal to x square of t. We have to check whether this particular system is going to be stable or not. So x of t and y of t. For x of t is equal to 1, the output is going to be 1. For x of t is equal to 10, the output is 100. For x of t is equal to 100, here it is 10 power 4. For 1000, you will get 10 power 6. Now can you say that the system is going to be unbounded? Okay, I mean to say the output is going to be unbounded. Okay, so system is going to be stable or unstable, but the signal can be bounded and unbounded. Correct. So we know that here all these values are bounded values because all of them are finite values. Are they infinite here? No. They are also going to be finite values. They are big values, but they are not infinite values. Correct. So here, for 1 it is leading to 1, for 10 it is leading to 100, for 100 it is leading to 10 power 4. Yes, it is leading to a huge values, but still it is going to be a finite value. So nowhere a bounded value of the input is going to lead to the unbounded value. So therefore, the system is stable. Let's look at any other relation. Y of t is equal to e power x of t. Y of t is equal to e power x of t, whether this particular system is going to be stable or not. Okay, the input is x of t, the output is y of t. X of t is equal to 1, here it is e power 1. So e power 1 is 2.7 something like that. So 2 here it is e power 2. E power 10, sorry, 10 e power 10. 100 e power 100. Now is it leading to the unbounded values? Yes, it is leading to big values, but it is not unbounded, right? Here, can you say any of the values is going to be unbounded here? There is no value which is going to be unbounded. All the values are bigger when compared to the magnitude of the inputs, but they are not unbounded values. They are still finite values, right? So therefore, this is also stable. Nowhere it is leading to the unbounded values of the output for the bounded values of the input. See, keep one thing in mind. Whenever you are testing the stability of a system, you should never give a particular input which is unbounded to test whether the output is going to be bounded or not. Because it is harsh on the part of a particular system that you are yourself giving an unbounded value of the input and you are checking whether it is going to be bounded or not. Okay? You should never do that. Because we always, whenever you are checking the behaviour criteria, bounded input, bounded output criteria, the input should always be a bounded value. You can never give a unbounded value of the input and test whether the output is going to be bounded or not. Okay, always the input should be a bounded value to test whether the output is bounded or not. Right. So that is a stable, unstable. Let us take one more example. Y of t is equal to t into e power. Let me change a little bit. E power t into x of t. Y of t is equal to e power t into x of t. I have to check whether the system is going to be bounded. I mean to say the stable or not. Y of t is equal to e power t into x of t. The input is x of t. The output is y of t. Now let us take the output. So the input value is equal to 1. The x of t is equal to 1. What is the output y of t? When the value of x of t is equal to 1, the output y of t is equal to e power t. 1, is it bounded? Yes. 1 is nothing but a constant, it is bounded. E power t, that is unbounded. Okay, so e power t into x of t is leading to a particular unbounded value of the output for the bounded value of the input. X of t is bounded, the output is unbounded. System is going to be unstable. Because the output e power t is going to be a unbounded value. Now you can ask me, what about the last one? So y of t is equal to e power x of t. How did you say it's going to be bounded? You can have a confusion, right? Why this particular system is stable, right? So here x of t here and y of t. If I take the value of x of t is equal to t, the output y of t is going to be e power t. Then yes, it's going to be an unbounded value of output. But you can see here whether the input is bounded or not. You can check whether the input is bounded or not. What is the input? A line passing through the origin. And the slope is equal to 1. Right? So here at t is equal to infinity, it is going to touch infinity. Correct. So this is an unbounded value. We cannot test stability by giving a unbounded value of the input. So therefore, this cannot be done here. For each and every value of x of t which is bounded, the output is always going to be bounded in this particular case. Therefore, we have given the system is going to be stable. But here the system, here I am giving x of t is equal to 1, the output is e power t, it is unbounded value. Now, let us look at the property of linearity. So based on the property of linearity, I can classify the systems as linear, non-linear systems. The system can be classified as linear, non-linear based on the property of linearity. Now what is the particular property of linearity? Mathematically, whenever a particular system satisfies a superposition principle, whenever it satisfies the superposition principle, the system can directly be said to be a linear system. So linearity is all about a superposition principle. Now the superposition principle has two subparts inside it. One is what we call as a scaling property or homogeneity. The second one is the additivity. Right? Now let us consider a particular system whose input is x of t and the output is y of t. The input is x of t and the output is y of t. Now what is this scaling property? The scaling property says that if you know that for the input x of t the system is giving you y of t, then a into x of t, where a is a scalar, the output of the system is a into y of t. Whenever you are scaling a particular input, the output should also be scaled by the same value. This happens in the case of a linear system. Okay, this is one thing. This is a scaling property. The second one is the additivity property. For that, we have to consider two inputs. The input of one is x1 of t and corresponding output is y1 of t. The input 2 is x2 of t. The output of the system, the same system, right? It is going to be y2 of t. Now, when you are adding both of them, x1 of t plus x2 of t, then the system is going to lead to the output which is y1 of t plus y2 of t. What does it mean here? Individually, an input x1 of t is leading to y1 of t, input x2 of t is leading to y2 of t. If you are summing both of them, if the input is nothing but addition of two inputs, then the output should also be addition of both corresponding outputs. Okay, individually you are getting y1 of t, y2 of t. When you are adding x1 of t, x2 of t, then the output should also be the addition of y1 of t and y2 of t. Okay, this is what we call as a property of additivity. Now, combining both of them, I can say that a1 x1 of t plus a2 x2 of t, whenever it gives you a1 y1 of t plus a2 y2 of t. When you know that x1 of t is giving you y1 of t, x2 of t is giving you y2 of t, then a1 x1 of t plus a2 x2 of t should always lead to a1 y1 of t plus a2 y2 of t. Okay? This is what we call as a superposition principle, which contains both scaling property as well as additivity property. Right? So this is what we call as the superposition principle. A signal, when it satisfies the superposition principle, okay? I mean to say, the system when it satisfies the superposition principle can be said to be a linear system. Now let us look at an example. So y of t is equal to 2 into x of t plus 3. Y of t is equal to 2 into x of t plus 3. Whether this particular system is going to be linear or not. Okay. See, please keep a note. The important note is that when we said about the scaling property, that x of t when it leads to y of t, a into x of t has to lead to a into y of t. There, the value of a that you consider and also the signal x of t can be complex values as well. Okay. Keep a note and write down a and x of t. I mean to say that a, let me write in words that the scalar and signal, scalars and signal can be complex. The scalars and signals can be complex values as well. Right. So let us look at this particular example. I just want you to pause the video and try to do on your own self whether this particular system is going to be a linear system or not. Okay, now let us look into it. So x of t, when it is given the input as to the system, it leads to the output as y of t. And the y of t is nothing but 2 into x of t plus 3. First of all, let me verify the scaling property. So, when x of t gives you y of t, the scaling property says that a into x of t should give you a into y of t. Correct? So, for this particular input, what is y into y of t? That is nothing but a into y of t, which is nothing but 2 into x of t plus 3. So, what I expect from the system is that the system output, whenever I am giving the input as a into x of t, the system output has to be 2a into x of t plus 3a to satisfy the scaling property. But let us see whether it is possible or not. For that, please tell me what is the output of the system. The output of the system is y of t, which is nothing but the system is basically multiplying the input with 2 and then adding a 3. Okay, to technically say, the system function is nothing but amplifying the signal by 2 times and then clamping the signal or adding the DC component of 3. That is the system's function here. So whatever input that you provide to this particular system, it is always going to amplify it by 2 times and then add a DC value of 3. That is what the system function is. Now, if that is the case, when I give an input as a into x of t, whatever be the input that I give to the system function is that it is always going to multiply the input whatever I give with the of 2 and then add the value of 3. So basically the system performance is this one. Now we have to judge whether it is going to satisfy the scaling property or not. So here a into x of t is leading to 2a x of t plus 3. Is that equal to a into y of t? A into y of t is nothing but 2a into x of t plus 3a. Here I have 3, whereas I want to get 3a to satisfy the scaling property. So it is not equal to that of a into y of t. So therefore, it is not satisfying the scaling property, so you can directly say the system is non-linear. You can directly say the system is going to be a non-linear system. So this is the property of linear, non-linear. And let us now look into the last property, which is time variant and time invariant. So time invariant and time variant system. What do you understand by the meaning of time invariant and time variant? Time invariant, please see, so many students understand that time invariant means the system output is not going to vary with time. That is time invariant. If it varies with time, it is going to be time variant. But that is not wrong, not correct. It is wrong. The meaning of time invariance here is that the characteristic of the system. For example, if I talk about the system as amplifier, the characteristic of an amplifier is nothing but it strengthens the input. If the amplification factor is A, that is a characteristic of an amplifier. Now, that particular characteristic should not change with time. Whether you give signal today, or you give it tomorrow, or after 10 days, or after a year, the amplification factor should be the same. It should not vary at all. Maybe after 10 days, the amplifier works as an oscillator. It's not a time invariant system. So whenever the characteristic of the behavior of a system, if it does not vary with time, such a system is what we call as a time invariant system. When it varies with time, we call it as a time variant system. So system's characteristic, the system's characteristic should not change with time. That is what we call as a time invariant system. Now let us take an example as y of t is equal to t into x of t. I want to verify whether this particular system is going to be time invariant or not. For that, we have to know the process of testing whether the system is going to be time invariant. Now please understand, it is basically that we are testing that whether the system's performance today and tomorrow, whether it is going to be same or not. For that, to test this particular criteria, what I am trying to do here is that one, the same input I am going to give it today and also tomorrow. If I give an input today, I should get the same output. Okay, I should get the output. If I give the same input tomorrow, I should get the output same as that of the previous day. But only thing is that there should be some delay, right? Because I am giving it tomorrow. If I give it today, the output that I am going to get, if I give it tomorrow, it means that the output should be same as that of the output that I have got yesterday, but the only difference is that I have to get it tomorrow. Correct? So, when the input is x of t, if the output is y of t, if I give it, for example, this is today. Now, tomorrow, it means that I am giving some delay to it. Correct? When the input is given some delay, it means that it is going to be in the future value. So something, the signal that is happening today is going to happen tomorrow. It means that there is going to be some delay. Correct? I should get the same output. If I am giving the same input, it means that the output should also be the same. So I should get the same, but with the same delay that I am giving here. So it should be y of t minus t naught. This is what I want to test. For an input x of t, if the output is y of t, for the input x of t minus t naught, the output should be y of t minus t naught. Right? So the same delay should be there. You should not get y of t. For x of t minus t naught, you should not be expecting y of t, right? It is like that. For today, for tomorrow's input, you are expecting to output today. That should not be the case. Right? So when I give x of t minus t naught, the output should be y of t minus t naught. So what I generally do is that for the input and output which are given here, for example, here you can see that y of t is given. I will calculate the value of y of t minus t naught. Okay? So I will just calculate the value of y of t minus t naught. And then I will assume that let x of t minus t naught is equal to x1 of t. I just assume that x of t minus t naught is going to be x1 of t. So when the system is given x1 of t as an input, the response of the system should be equal to y1 of t, and I want this y1 of t should be equal to that of y of t minus t naught. So when this is satisfied, the system is going to be time invariant system. When this is not satisfied, I mean to say that when the value of y1 of t, if it is not equal to the of y of t minus t naught, then it is going to be a time variant system. It is going to be a time variant system when the value of y of t minus t naught, okay, why mean to say y1 of t is not equal to that of y of t minus t naught, it is going to be a time variant system. Okay, let me apply the same to the example that I have taken. So it is very clear that for the input x of t, the output y of t is going to be equal to that of t into x of t. For input x of t, the output y of t is nothing but equal to t into x of t. So for x of t minus t naught, the output y of t minus t naught, okay, if you want to calculate y of t minus t naught, you just put in the place of t, t minus t naught. So if I put t minus t naught here, it should be t minus t naught into x of t minus t. Correct? If I want y of t minus t naught, it means that y of t minus t naught is equal to, in the place of t, I am putting t minus t naught. So t minus t naught into x of t minus. Right? So now I am going to give x of t minus t naught as equal to x1 of t. When I give the input as x1 of t, what should be the output? The output is y1 of t. What should be equal to? You have to understand what is the system doing actually here. The system, what it is doing is that whenever I give the input as x of t, the system is basically multiplying the input with that of t. The system is basically multiplying the input with that of t. That is the system's function here. So every time you are giving the input as x of t, the system is nothing but multiplying t with that of x of t, nothing else. So if that is the case, if I give the input as x1 of t, the output y1 of t is going to be equal to the of y1 of t is equal to the of t into x1 of t. The output y1 of t is equal to the of t into x1 of t. What is x1 of t here? x1 of t is nothing but x of t minus t naught. So it is equal to the of t into x of t minus t naught. T into x of t minus t naught. Now you have to check whether this is equal to the of y of t minus t naught or not. Now what is y of t minus t naught? It is equal to t minus t naught into x of t minus t naught. Is it equal to the of y1 of t that I am getting here? No. It is not equal to the of y of t minus t naught. So therefore the system is going to be a time variant system. The system is going to be a time variant system. So here this particular system is a, okay. Now you can check it with the of y of t is equal to x of minus t, whether it is going to be time invariant or not. Okay, I'm just giving you the answer. This is also going to be a time variant system. Okay, you can just check it. Okay, students. So now we have seen about all 6 properties, right? We have started with the of static and dynamic systems, and then we have seen invertible, non-invertible systems. Then we have seen causal, non-causal. Then we have seen invertible. We have seen stable, unstable. Last 2 properties are linear, non-linear. The last one is a time invariant and time variant. So these are the 6 very important properties. And we have seen that so many times the questions have been asked from this particular topic of system properties. So let us see some gate examples. So if you have any problems in understanding any of these particular properties, that will be clarified in this particular gate problems. So students, you can try to solve this particular problem. It is given that y of n, the output, is equal to sine of 5 pi by 6 n into x of n. We have to check 3 properties: linearity, stability and invertibility. Okay, so different options have been given here. So you have to pick one of them as the right answer. Okay, you can pause the video and try to solve it. Okay, let us look at the solution here. First thing is that I want to check whether the system is going to be linear or not. Okay, so the input is x of n. The output of the system is nothing but y of n is equal to that of sine of 5 pi by 6 n into x of n. Right? So I can check the scaling property. So a into x of n should always give me a into y of n. A into x of n should always give me, this is nothing but the scaling property. It should give me a into y of n. So what is the system's work here? The system's function is that whenever I give the input as x of n, the output is nothing but it is going to multiply the input that I am giving with it of a sinusoidal signal. That is the system's function, nothing else. The output y of n is nothing but whatever input that I am giving x of n, that is multiplied with it of sine of 5 pi by 6n, a sinusoidal signal. That is what the system's function is all about. So when I give a into x of n, this is the input. What is the system doing? The system is going to be multiply sine of 5 pi by 6n to the top the input that I am giving. That is nothing but a into x of n. So this is the system output whenever I give the input as a into x of n. Now you have to check whether this is equal to the of a into y of n or not. And then if you observe here a into y of n, if you know the y of n, a into y of n is nothing but a into sine of 5 pi by 6n into x of n. So whatever you are getting here for the input of a into x of n is actually going to be linear because, or satisfying the scaling property, because this is equal to the of a into y of n. It is satisfied. So therefore it is satisfying the scaling property. So once it satisfies the scaling property, it will satisfy even the linearity, I mean to say the additivity property. So therefore, by just checking the linear, either the scaling property or the additivity property, one of them, you can easily say whether it is going to be a linear system or not. Here it is satisfying the scaling property, so I can directly say that it is going to be satisfying the, it is satisfying the scaling property, so directly I can say that it is satisfying the linearity property. So system is definitely going to be a linear system. So linearity is checked. Now stability, whether the system is going to be stable or not. We have already seen how to check the stability of a particular system, right? So when the input is given as x of n, the output y of n, right? So whatever value you are getting here, giving here 1, 2, 3, 10, 100, the output is going to be equal to the of 1 into sine 5 by 6n, 2 into same, 3 into same, 10 into same, 100 into same. So for no value of the bounded input, you are actually having the unbounded value of the input, because 1 into sine 5 by 6n is going to be bounded value. This is also bounded, third one is also bounded, fourth one is also bounded. So it means that the system is actually having, for every bounded input, the output is bounded in nature. So system is stable. So linearity, yes it is linear. Stability, yes it is stable. Now the last one is invertibility. I think similar problem has been tested already, right? So in the example that we have considered, we have taken a similar example. You can take the value of x of 0, okay, x of n. So when the value of n is equal to 0, x of 0, the output is going to be equal to x of 0 into sine 0. It is going to be 0 itself. Similarly, you can take the value of n is equal to 6. So when you take the value of n is equal to 6, you will have sine 5 pi is equal to 0. So for the value of n is equal to 6, x of 6 is also going to give you 0. So it is going to be non-invertible. The system is linear, stable, but not invertible. So the answer is option C. So dear students, here you can see that there are three properties which are given here. First one is that linear but not time invariant. Second one is that non-linear but time invariant. Third one is linear and time invariant. Four relations are given. Okay, the first one is y of t is equal to t square into x of t. Second one is y of t is equal to t into mod of x of t. Third one is y of t is equal to mod of x of t. The last one is y of t is equal to x of t minus 5. So based on the properties of linearity and time invariance, this question has been framed. Okay, it's a match the following question. You are given four options, you have to pick one of them. Okay, you can pause the video and try to solve the problem. Okay, so the approach is that you are given four relations, right? So you can take each one of them and you can test the linearity and time invariance. So the first one, linearity, right? So R1 you are testing the linearity. So what is the system doing here? The system, when you are giving the input as x of t, the output of the system is nothing but it is multiplying the same input x of t with it of t square. That is the function of the system. So when the input is x of t, the output is going to be equal to y of t, which is nothing but t square into x of t. Now using the scaling property, you have to just check whether the a into x of t is equal to a into y of t or not. This is the scaling property. Now practically you are taking the a into x of t. Now what is the system's performance? System is always going to multiply your input with it of t square. So t square into a into x of t, which is your input, which is a into t square into x of t, which will be equal to that of a into y of t. So the system is linear. What about time invariance? The system is going to be time variant. I can directly look at the question and say whether it is going to be time invariant or not here. Why? Because whenever you have the output y of t, it's a very important point that whenever the output y of t is nothing but input multiplied by any function of time. Whenever the output y of t is nothing but input multiplied by any function of time, the system is automatically a time variant system. The system is automatically a time variant system. So it is going to be a time variant system. So now I can directly say that the first two relations are going to be time variant relations. So anyways, you can see that this particular system R1 is going to be linear, but it is not time invariant. It is going to be time variant or it is not going to be time invariant. So P1 is going to go with the of R1. P1 goes with the of R1. You can eliminate the two options here. So now let us look at what about this one, because here we are very much clear that it is going to be a time variant system or not time invariant in nature. So I want time invariant nature, right? Do we have a time invariant nature in these two options? We don't have a time invariant nature. So R2 should never go for P2 and P3. You can just see that. Okay, in the two relations, there should never be R2. Okay, because this particular R2 is going to be time variant, right? But where these here, none of them is going to be time variant. Okay, here also time invariant, here also time invariant. I can see here that in option D, R2 is going with it of P2. What is P2? Non-linear time invariant. But it is not going to be time invariant. So I can eliminate the option D also. So option A is going to be the right answer. Okay. So it means that P1 goes with R1, which we have already seen. P2 goes with R3. Non-linear time invariant goes with the of y of t is equal to mod of x of t. Is going to be non-linear. Okay, you can check it. Okay, whatever we have discussed, using that you can check it how it is going to be non-linear. It will be non-linear, but it will be time invariant. Whereas the last one, R4, is going to be linear and time invariant. You are just simply considering a delay, the time shift. It is going to be both linear and time invariant operation. So hope the class is very helpful to you. Thank you for listening and all the best.